Okay, welcome to Biostatistics and Experimental Design. This lecture is on variable and model selection. So this is a relevant issue if you're studying something that we know is influenced by many predictors. And just to be timely, let's talk about COVID and the probability of surviving. So we're going to have surviving COVID. And what are the factors we think go into surviving COVID? We know that increasing age decreases the chance of surviving COVID. Having diabetes, having pre-existing heart conditions, okay, and I'm just going to throw this out there. Smoking. Okay, this is a respiratory illness, so I can imagine smoking increases your chances. So here are 4 things, and we could imagine there might be many others to throw in here, but let's just stick with these 4. And you are tasked with, people want to know, well, what's really driving survivorship? Are all these things equal? Should it be weighed any differently? How do you come up with a best model? Historically speaking, historically, we'd have one model, and we'd be most interested in examining these variables and only including those variables, which I'll just call vars, only include those variables that were significant, okay? In other words, they're coefficients. They're not equal 0, okay? So if they were statistically significant, their coefficients were statistically significant and different from 0, then they would be included in a final model, okay? A more modern approach, okay, is model selection. So variable selection, you get one model. So a modern approach is a multi-model. And it also uses information. How much information? So historically, variables would compete. The multi-model view of how we figure out what to use is the information content, okay? And this idea of parsimony, okay? And this is also goes into the historical aspects as well. Parsimony is this idea of explaining the most, okay, with the fewest parameters. Okay, explaining the most with the fewest parameters. Okay, your model should be simple, but not any simpler. Okay, we don't want to make them too simple where they miss salient features that would increase our power to explain. So that's our task, is how do we assess different models of surviving COVID? Because maybe just one or a combination of 2, or maybe some of these things interact as well. We need to include the interaction. All right, so let's look at age, for example. And we want to know the effect of age. Whoops. The effect of age, okay, our explanatory variables go down here, on surviving COVID, okay? So surviving COVID, so S sub COVID. So what's our probability? So if we are young, you know you have much higher chances, okay? And I think if we were to look at the data, so we know that it's not perfect though, because we know, for example, that there are people, unfortunately, that pass away. But as you get younger, older, the probability of not surviving, okay, goes down. So there's different ways we could model this, okay? So let's just pick on age for a minute, and we'll pick a simple model, okay? So let's draw a line. And we could say, how can we fit a straight line to this data? So it might look something like this, okay? So if we did draw that line, okay, a simple single parameter. So we'll have S equals, and then we have some intercept, okay? So we'll call that mu plus the effective age, okay? And this is the slope, this beta, okay, plus error, okay? So survivorship, you know, there's gonna be some mean survivorship across the whole thing, and then our effective age, okay? And we know that is a negative, right? We suspect it's negative. So here we have a nice linear thing. With a single parameter like this, it looks like we would never fit observations over here correctly, and we would never fit new observations. So if we, even with scatter, if we get new observations, they're likely always to be missed by this line. Maybe in here they get hit by that line, okay? But over here, again, they get missed. So this line has bias, significant bias, if we add in another parameter. And with age, that other parameter would be a squaring term. And what squaring does is it puts a bend. So we can put a bend in this, okay? And we can say that maybe goes something like this, okay? This model looks like this. This is a simple quadratic model. So it's age plus, let's call this beta 1, beta 2, age squared plus error, okay? So if you notice, our points that we get are going to be much better described, okay, by having that age. But again, we're not getting everything. So what drives this point above the line and what drives this below? So it's something about the age is kind of capturing it, but it's also missing a bunch, okay? So what could we grab, okay? If we go back to our other variables, we could always add in another variable, okay? We can add so many variables that we get, let's redraw this, same axes. Let's just put in a few points, okay? But with the same shape. We could add in enough parameters that our line fits all the points, okay? So this has as many variables as there are observations, okay? So that would have as many variables as there were observations. The problem with this is that if we were to add a new observation, they would never fit on our line, okay? So where bias was here, they wouldn't fit on the line because we have the wrong line. Here, we've overfit, so no new observation is going to hit the line. We increase the variance. If we examine now, going between extremes, okay? Going between extremes, so let's look at model complexity. Okay. If we look at model complexity, we had maximum bias with a very simple model. In fact, we can get rid of age and just do an intercept model. Okay, we can just look at these points and fit an average. So we can go even simpler, but what we'll find is that bias will tend to go down as you increase model complexity, okay? So this is bias, okay? So we want to reduce bias, that's great. So we want to make our models more complex, we get rid of bias. But a competing problem is that the variance increases. So a simple model is applicable to all observations and we lose that. And what happens is our variance, right, in future observations increases with model complexity. Model complexity. All right, so this is one source of error. This is another source of error. So our total source of error is these two curves added together. Okay, so total error. Okay, and by error, I mean in predicting new cases. Okay, so we could work out our model and then somebody comes to us and says, what's their probability of surviving? We could ask them about their age and plug in this model and come up with a prediction. And we do that over and over, and this would be our error, okay? So what we're shooting for in parsimony, okay, is this sweet spot, okay? And every variable will alter the shape. This is heuristic curves. They don't actually look like this. They can take on slightly different forms. But what we're looking for is reduce the total error, okay? So this would be the most parsimonious model, right? When we talk about model complexity, right, over here is simple models. So we'll call this like U only. So these are also called intercept only models. Okay, all you do is fit the average, right? The average response. So what's the probability of someone surviving would be just ignoring age and just figuring out, you know, it's, I think it's 3% right now. It's 10% if you're older, 1% if you're younger. But overall, the average is about 3%. But that doesn't explain things well if you know their age. If you know their age, you can explain things much more. On this opposite end, right, you have full models, okay? So full models account for every observation. And this in the middle would be somewhere between explaining every observation and explaining only the average response. So somewhere in here is the sweet spot. We call this side of the curve underfitting. Okay, we haven't explained enough and we miss a number of predictions because we just don't have the right model. On this side, we've overfit, and so any new observations will be missed, okay? So this is the sweet spot, what we're looking for. We don't expect our predictions to be 100%, but we shoot for the best. In fact, we always shoot for reducing this term. If we can reduce this term, that means these terms are doing their best, okay? If this becomes larger, it means we've taken things away from the explanatory variables and moved them to error, okay? So let's pause for a second. Okay, in our attempts to find parsimonious models, even in the view of variable selection, right? So only including those variables which were statistically significant. We used to be into something called stepwise selection of variables. Stepwise selection. And you could sound like a dance. You could forward, you could backward. And there were other methods too, where you could simultaneously look at all variables at once. What forward selection does, it would look at your response variable, add in the intercept, and just start adding things. So it might add in age, okay? And it will look at this beta age. If it did not, if this was not statistically significant, it would boot out age and then add another variable, let's say diabetes, okay? And would look, is this statistically significant or not? And by statistically significant, it means that the coefficients equals 0, okay? So if it was statistically significant, it meant that that beta, that effect, was more than 0, okay? And it will go on and keep adding until nothing else you could add was more significant. Backward selection, you threw in everybody okay, and so on and so forth. And what it would do is, now that you have everybody, it would look to remove variables. But here's the thing, for both these techniques and why we largely don't do them, it's sensitive to the explanatory variables and the correlation between those two. And we know, for example, that as you get older, you're more likely to have diabetes. When you alter the model, okay, when you remove age, it takes some of that variation that was explained by age and puts it into other variables that are correlated, even if it's a small correlation. It would move that variation over here and make them more likely to be significant. So it wasn't as if these p variables were fixed, you know, independent of each other. When you messed with the variables, it altered the p values as you went along. And but that's the best thing we had. And you still see these methods out there. Stepwise selection still out there, so you should know what that is. Okay, and again, it's sensitive. These methods are sensitive to something called multi-collinearity. So, in other words, correlations. Okay. So multicollinearity is when your explanatory variables, okay, are correlated with each other in terms of your response variable. Okay. So that is stepwise selection. All right. So as I mentioned before, examining models is way more popular now. So let's take a look at that. okay? And let's say you have one variable you're interested in, okay? So let's look at, you want to know your survivorship. We're just going to call Y here. We have our intercept, and here we have our intercept plus age, okay? And actually, let's alter this a little bit. Let's say we know that age is important, right? So beta age, it's not beige. This is beta age. And then we have our beta age squared. So remember what squaring does. It adds a curve. So for example, we want to know, so this is just age, and this is age squared, okay? So we want to know, does adding this curve actually help things or not, okay? And if we only have two models, okay, and I altered this a little bit differently than just the intercept, because this is a common question of whether you should add in these curvilinear effects that seem to bend things. We can do what's called a likelihood ratio test, okay? What is the likelihood? If you remember, the likelihood is how well a model, I'm sorry, how well the data fits a particular model, okay? And if you remember, right, it's the probability of every observation given certain parameters, such as these means. So what's the likelihood of observing these data given this mean and the overall mean? So the likelihood ratio test, okay, examines, just like it sounds, the ratio of likelihoods, okay? And the formula for that is chi-square. So it's a chi-square distribution, -2, and it's the likelihood ratio. So I'm going to use a cursive L of the more complex let's get rid of that, and let's call it the more complex model over the likelihood of the less complex model, okay? And if you want to think about this, and it's tested with 1 degree of freedom, okay? So that's all you have is 1 degree of freedom. So if you think about what this means, your critical values should be much greater than 2, -2. Why? If the likelihood, if you remember, the fit is so much better than the least complex or the less complex model, this ratio should be much higher, okay? So that's a relatively simple thing, and I would say this is a great tool to use if you're just asking this question, a linear model or a curvilinear model. And you can actually have, okay, you could look at this as an ANOVA as well. So we can say young, middle age, and geriatric, and survivorships may look something like this, right? This is still, since we're dealing with the intensity of a treatment, so these levels are the intensity, we can still fit a curvilinear model to these, even though it's in what we think of more of a classic ANOVA response, right, with 3 groups. You can still test these curvilinear models. Okay, the next thing we're going to look at is if you have a number of models. And by number of models, I mean more than 2. Although this can be used for 2 models. The AIC information criterion. Okay. AIC. Okay. And that's just a K. All right. AIC is named after a Japanese statistician. Hiro Google AIC. He was born in 1927. And rumor has it he came up with AIC while riding on a train to teach. I don't know how true that is, but it makes for a good story. Okay, let's get into what AIC is and how we can use it. So AIC is equal to 2 times the log likelihood plus 2K. All right, so let's think about this. If we throw up our curve where we looked at bias and we looked at variance, okay, and we want to find the model here, okay, and this is model complexity. Okay, so bias has to do with model fit, okay? And we know that likelihood is a way to measure model fit, okay? So moving this way, we're gonna increase model fit, okay? So that's this part of it. This 2K, K refers to the number of parameters, okay? The number of parameters. So as you move this way, you're adding, as you become more complex, you're going to add more parameters. So for example, if we're looking at COVID survivorship, we could say with age, with diabetes, with smoking, et cetera, we're becoming more and more complex, right? We're going to add those parameters are going to increase our K. This negative, okay, here, this means that the better the model fit, the smaller we get, okay? But if we do it at the expense of adding parameters, the larger we get, okay? So the smaller the AIC value, the better, okay? And let's just say it's all relative, okay? Because we're letting models compete, and every model, right, varying complexity will have different AIC values. So we're letting models compete with each other to do their best explaining the dependent variable. Okay, so how does it work? What do we do? All right, so let's get rid of some of this. So likelihood is a number that will be generated by your software. In fact, AIC is generated by most statistical software, so it's not something you'll actually have to measure, right? what you want to do is sit down and think of your best models that you want to look at. So let's say we're looking at COVID survivorship. We think age is it, okay? But you've also heard that age and diabetes, okay? Age and diabetes are important. And then we have to consider is maybe these two things interact. So that would be age by the interaction, okay? And maybe you have age and smoking. Okay. And so we think these are our most important variables, okay? So we're gonna let these variables fight for the top, okay? I wrote this in order of how I came up with them, but that's not how the data may play out. We should also throw in an intercept only. Okay, because maybe, right, we're just fooling ourselves because we can end up with a top model, but maybe top model doesn't do anything for us, right? Dealing with complex phenomenon, sadly to say, the intercept only is a good way to sort of assess if you just have just a pile of junk and you found the prettiest piece. Okay, so intercept only, including that in your pool of models, is really important. Okay, so what you want to do is, let's put this over here, select models, right? And you want to select models that you want to select models that you can justify. Okay, you would not put in here how many times they watched Tiger King. Okay, maybe it does, but I don't think that's kind of a spurious model. So you want to select your models plus intercept only. Okay, so now you have your pool of data that you did a priori. 2, you run the models. An important caveat is that all have the same response. Okay, what do I mean by that? So we're looking at the probability of survivorship. We have to keep that constant as we let it be explained by these different models. We can't say the probability of survivorship here and then take the log of the probability of survivorship, because now that is apples and oranges, right? So we run all models and they all have the same response, right? Because they're fighting to explain that one response variable. So if you alter the response at all, you kind of muck that up, okay? Then you want to get, so 3, you want to list and sort your AIC values, okay? So let's say our AIC values, I'm really gonna make these numbers up. I have no idea. So what do we know though? We know that the smaller is better. So let's just first list these. 558. Okay. So here's our listing of AIC values. And what we want to do is arrange these and put them in order. So our smallest AIC was what? Was this one here, okay? So we're gonna say, let's call this model 1, okay? So model 1 had an AIC value of 558, okay? Model 2 at 560, okay? Our next in line, 562, all right, M3. 562, who's next? Age, all right. That we're gonna call that M4, so model 4, 570, and that leaves M5, so age plus smoking. It's 590. All right. So here's our sorted AIC, right? So AIC, and this is our, what we call the minimum, okay? The minimum AIC is this guy right here. Then we want another column, and we're gonna call that delta AIC min, okay? So remember that delta is the difference, right? So this is the difference between model I and the AIC of the minimum model, right? So M1 is minimum model, and we look at the difference between that and itself, so it's 0. Okay, and this is 2. So, and then we just go down. So to get from here to here, 562, that would be 4, and then should be 12. Right, so 12 plus this 570, yes. All right, and then we're looking at 32. 32. Okay, so how do we take these numbers, right? So we list and sort our AIC, okay? Calculate delta AIC min, okay? And we'll just say that that is AIC I minus AIC min. Okay, we're looking at this difference here. Okay, 5 interpret. Okay, so there's the steps we do. How do we interpret? The model that ends up being the top model, the min, is our top model. Okay, so let's make some space. Can't do it there. All right. So let's just, I'll do this. So this is our top. Okay. And the distance in AIC units, okay, this is why it's all relative. So if I just told you some model had an AIC of 570, that's meaningless. If I told you the top model had 558, now that's meaningful. As you get farther and farther from the top model, you explain less and less and less, okay? So what we consider as a general rule of thumb, so AIC values 0 to 2, we consider them to be similar. And here's the thing, is that that doesn't matter if it's the top model and the next top or somewhere in here. Any two models within 2 units are considered similar, okay? From 2 to 4, they're okay. And this is just a rule of thumb, okay? And then 4 to 7, I will say these are meh models. Greater than 7, don't consider. Okay, so right off the bat, M4. Who is M4? Age, no, 1, 2, 3. It was just age, okay? So there's our M4. So just age, we can get rid of, okay? And M5, age and smoking, we can get rid of, okay? That's not to say these variables are not important, but that model. So age and smoking together and just age by itself, okay? And here's an important thing. Let's get a measure of where our intercept was, 562, okay? So there's our intercept. So what we're saying is that these models performed worse than just saying what the average was. So these are actually very misleading models, and that can happen, right? Again, I made up these numbers, and I don't know how true any of this is, right? But these numbers perform worse than just plotting the average, okay? That's not good. When your intercept is within 4, so I kind of did this on purpose because it's a nice discussion. Ideally, your intercept, of course, is greater than 7, which means you did a good job of picking variables and thinking about models and how they affected your response variable. If your intercept is up there, okay, so it falls within okay. So here it falls within 4 AIC units of our top model, which means it's in the running, okay? This means that our pool of models is probably incomplete, right? That unless survivorship is just completely random, we probably have not discovered the variable that's really driving survivorship. I don't know if that's true or not. But anyway, in our simulation here, the intercept is 4, which means this is good, but it's not super awesome, okay? We've explained more than random, but not too much more. So we'd have to think about this some more. So let's just remember this. So who is M1? M1 was age, diabetes, and interaction. And 2 was age and diabetes, okay? So here's our top model. So given these two are close, okay, and the only difference, okay, is this. I'm sorry, this interaction here. That's telling me that by adding the interaction, we actually didn't increase things that much. We could actually ignore interaction and still pretty much get the same model. Unfortunately, if we got rid of that, then you know, this would make this the minimum model. This would be 0 now. This would be 2, which means our intercept is creeping up even better. So what we have is a group of relatively weak models, okay, with some good evidence, okay? This no longer is like black and white and p-values, but really shades of gray, and that we have good evidence that our top model is a good model. It doesn't do much better than a more simple model, and both are okay, but because the intercept is up there as well, these are relatively what I would consider weak models. And hopefully I don't wish this upon you, because it means that you still have to go hunting for more data. Okay, let's stop there.